Hello dear students and colleagues, my name is Bauyrzhan Sarsenuly and I am a teacher of physics in Isobaric Intellectual School of Astana, and welcome to my video lesson that known as gas laws. So let's start our lesson that known as gas laws. Learning objectives of this lesson are to enable students to understand the ideal gas laws, deduce a relationship between pressure, volume and temperature, and finally apply the ideal gas law to relate and calculate values for pressure, volume and temperature. Vocabulary that you will need during this lesson is presented in this table in 3 languages: English, Russian and Kazakh. The words are isoprocess, pressure, temperature, volume and gas, for which you can find a translation in both languages, Kazakh and Russian. Before we start to talk about gas laws, let's recall knowledge about ideal gas, its properties and physical quantities as pressure, volume and temperature of a gas. So, in this simulation, we can observe a behavior of gas molecules in a container with the help of inserting a gas molecules with the help of a pump. We call the gas ideal if the molecules do not exert any forces on each other and their collisions with the wall of the container are fully elastic. Many real gases show behavior that is a very close approximation of ideal gas behavior. As a result of collisions between the molecules and the walls of the container of the gas, pressure develops. Pressure, volume, temperature, and the number of moles in the gas are related through the ideal gas law. Application of the laws of mechanics to the motion of the molecules leads to the connection between the average kinetic energy of molecules and the absolute temperature of the gas. Let's talk about gas laws in more details. The process that runs at a constant magnitude of one of the parameters known as isoprocess. From the Greek word isos is known as equal. The processes are isothermal process, isobaric process and isochoric process. In case of isothermal process, temperature is constant, isobaric process, pressure is constant, and isochoric process, volume is constant. One of the main empirical ideal gas laws was established in 1662 by Robert Boyle and independently in 1676 by Edme Mariotte. Therefore, this law is known as Boyle-Mariotte law. This law states that the volume of a given amount of gas held at constant temperature varies inversely with the applied pressure when the temperature and mass are constant. Mass constant thus means that mass depends on a number of moles in a gas. Let's look at the graphs that represent this law. In this pressure-temperature graph, we can see that pressure and volume are inversely proportional to each other. And if volume decreases, pressure will increase, and the number of collisions of particles with the wall of any container will be increased. If we will choose 2 dots on line of the graph and draw lines to the pressure and then to the volume, the areas of these 2 squares will be equal to each other. That means that a temperature is not changed, it is constant. As represents this figure with a piston, container and particle inside it. When volume decreases, pressure increases and vice versa. Let's, for example, imagine a system that consists from a container with a piston. There is a gas inside a container and this container placed into a lake. Here, lake works as a heater in order to maintain the temperature of the gas inside the container to be constant. If we will slowly add a weight on the top of the piston of the container, the volume of a gas inside the container will start to decrease and pressure will start to increase, as the number of collisions of molecules with the wall of the container will increase. This is an example of how either thermal process does work. Now let's do an experiment. So, isoprocess is one of the interesting parts of teaching physics, and there are so many ways to demonstrate experiments for students where they can understand the process itself, and in the future they can apply their knowledge. It's a main part of teaching physics, you know. So, as for the Boyle-Mariotte law, or in other words, isothermal process, I will need to use the next equipments. So, I will use pipette, 2 iron plates, 3 screw clippers, and colored water. So, isothermal process, it's a relation between pressure and volume. Therefore, first of all, I will fulfill this pipette with the colored water. So, I need to release all the gas inside it to fill it completely. Now I need a space. Now I need a space. This space is have a same cross section. I mean diameter is the same, so I can use it to demonstrate how volume changes when pressure increases. So I will use this pipette, and my volume will measured in length. When I will increase the pressure on this side of the pipette, the area will decrease. I mean volume of the empty space will decrease as I will insert a force. So therefore my volume in this experiment will measure in length, and pressure will measured with the help of using a number of books. So as you can see, this experiment is very simple, and students can understand the process itself, how pressure relates on a volume itself. So first of all, to do this experiment, I need to squeeze this side of a pipette with the help of 2 plates and 3 screw clippers. I'll need a time to do it. Now finally, I squeezed one end of this pipette to demonstrate here when I will increase the pressure, the area of a gas, in other words volume, will decrease as pressure will increase. This process will demonstrate here relationship between pressure and volume. So next, let's measure the length empty space of this section of a pipette. So it's equal to 65 millimeters. So now I will make a dot here to show that a length is equal to 65 millimeters when there is no any books on the other side of the pipette. Now I will add one book, and we will observe how pressure will exert a force and our volume will decrease. Now we add one book as a pressure, and we can see that as pressure increased, the volume inside the pipette was decreased, and now it's approximately equal to 40 millimeters. So when we placed one book on one side of the pipette, the length of empty space was 39 millimeters. So one book, 39 millimeters. So it's our second dot of our line. So let's add one more book to increase pressure and decrease volume. We added the second book, and now pressure increased and length of a pipette of the empty space is equal to 27 millimeters. So as a result, when we added the second book, our length of empty space of the pipette is equal to 27 millimeters. So second book, 27 millimeters. It's approximately here. Yes. Now I added the third book, and the length now equal to 19 millimeters. So our next point will be when length is equal to 19 millimeters and number of books is 3. As you can see slowly, we have a pattern of a line of either thermal process. Now let's add one more book, please. So we added the fourth book, and now the length of empty space is equal to nearly 13 millimeters. When we added the fourth book, now length of a pipette was equal to 13 millimeters, so 13 nearly here, and the fourth book. Now, dear students and colleagues, we now can draw a line, resulting line of our isothermal process. We can see here direct relationship of pressure, that number of books, and length that was measured in millimeters. Now we can see that students also can understand the relationship of the pressure and volume, in other words, Boyle-Mariotte law. Okay, dear students and colleagues, first of all, let's visualize our problem by drawing a picture of a lake and a bubble inside a lake. So it's a lake and we have a bubble at the bottom of a lake. So its volume is V. So as our bubble goes upwards of a lake, its volume increases 4 times. As for pressure of the bubble at the bottom of a lake, it's equal to the pressure of atmospheric pressure and plus pressure of a lake. As it goes upwards, its pressure decreases, and pressure of the bubble at the top of a lake is equal to atmospheric pressure. According to our problem, atmospheric pressure is equal to 100 kilopascal. That's equal to 10⁵ Pascal. And density of our lake is equal to 1000 kilogram per meter cube. Volume of air bubble at the bottom of a lake is equal to its initial volume, and volume 2 is equal to increasing of a volume at the top of a lake. It increased 4 times according to our problem. And our task is to identify the depth of a lake. Let's symbolize it with the letter H. Height of a lake. So, in our case, we have difference of pressure and difference of volume in case of constant temperature. Therefore, we can use equation of Boyle-Mariotte that equal to pressure 1 multiplied volume 1 equal to pressure 2 multiplied to volume 2. In our case, pressure 1, as I said before, is the summarization of atmospheric pressure and pressure of the lake. So pressure 1 equal to pressure atmospheric and summarization of pressure of a lake that equal to density of water multiplied gravitational field strength and multiplied height of a lake. And pressure 2 is equal to atmospheric pressure, pressure 0. So, as volume changes as it reaches top of a lake, we can write as pressure 1 multiplied volume equal to, initial volume equal to pressure 2 multiplied to volume as it reached the top of the lake. That means that it increased its volume 4 times, multiplied for V. So we can cross out V volume, and we will have, I will continue calculation of this problem as the next page. Therefore, as a result, we will have pressure 1 equal to 4 pressure 2. So our pressure 1 is equal to atmospheric pressure plus a pressure of a lake equal to 4 multiplied to atmospheric pressure. So in this case, we can subtract pressure, atmospheric pressure, and we will have, as a result, we will have rho GH equal to 3 multiplied to atmospheric pressure. So from this equation, we can find a height of a lake. So height is equal to 3 multiplied atmospheric pressure divided on density of a lake and gravitational field strength. So 3 multiplied to 10, 5 powers. Density of a lake is equal to 1000 kilogram per meter cube. And gravitational field strength is equal to 10 Newton per kilogram. So let's multiply 3 on 10, 5 powers, and divide it on 10,000. So we will have a result that equals to 30 meters. So the result of our problem is a 30 meters. It's the height of a lake. The next law is known as Isobaric process, when pressure is constant. This discovery was made by French chemist and physicist Joseph-Louis Gay-Lussac in 1802. Gay-Lussac law states that at a constant pressure, the volume of a given amount of gas held at is directly proportional to the Kelvin temperature. At this graph, we can see directly proportionality of the temperature and volume. It's found that the volume increases uniformly with temperature. It is said that if we will do experiments several times with a different quantity of a gas, or a gas at a different constant pressure, the result will be the same. In each case, a straight line graph of volume versus temperature is different. But the striking fact that when each straight line is extended backwards, it always crosses the theoretical temperature axis at 0 Kelvin, as it's shown in the graph. For the next laboratory work, I will use a balloon, beaker with the water that boils, and a heater. I will demonstrate here isobaric process. As temperature of this gas inside the air balloon will increase, it will expand, and volume of the air balloon will increase as well. So we will observe a relationship how temperature and volume is directly proportional to each other. As for now, the temperature of a gas inside the air balloon starts to increase, and its size, its volume will increase as well. You can see that its volume starts to increase. It does mean the number of collision of particles inside the air balloon start to increase and air started to expand, and average kinetical energy of particles also increasing.
In our experiment, our balloon is filled with gaseous air molecules. When the balloon is placed in the beaker with boiling water, the energy from the higher temperature water and steam molecules transfer to the lower temperature air molecules inside our balloon, exciting them. When the air molecules in our balloon are excited, by raising their temperature, they spread further and further apart, increasing the volume of space they take up. The higher the temperature or the more energy the air molecules get, the larger our balloon will grow, or in other words, the greater the volume of space our gas will take up. If we remove our balloon from the hot water, the air molecules inside our balloon will gradually lose the energy they've been given, dropping back to room temperature, causing the balloon to shrink in volume back to its original size. In the second portion of our experiment, we place our balloon in a freezer, which causes a transfer of energy in the form of heat from the warmer air molecules inside our balloon into the cold freezer. As the energy is removed from our air molecules, they slow down, drop in temperature, and get closer and closer together, decreasing the volume of space they take up. The colder the air molecules get, the closer together they will be. If the temperature of a gas is lowered low enough, it will go through a change in state from a gas into a liquid. When we remove our balloon from the freezer, the air molecules inside will gradually gain extra energy from the air in the environment, raising its temperature, causing the balloon to increase in volume back to its original size.
Okay, dear students and colleagues, according to our next problem, we have a constant pressure and volume that increases twicely as gas expands in a container. Let's draw a graph of pressure and volume. According to a task, we have a pressure that equal to 1.5 atmospheres. It's equal to 151,500 Pascal. And volume 1 is equal to 4 meter cube. And as our gas twicely expands, volume 2 is equal to 8 meter cube. So now we have a graph of pressure volume. The unit I will choose kilopascal and volume in meter cube. So I will just choose one line that I will write that it's equal to 151 kilopascal, and the pressure volume 1 equal to 4 meter cube, and as our volume increased twicely, it's equal to volume 2 will be equal to 8 meter cube. So as our pressure is constant, I will choose 2 dots and make a line. According to task of a problem, we need to identify work done by the gas when volume was expanded at a constant pressure. Therefore, work done by the gas equal to multiplication of pressure and volume. In our case, it's an area underneath of our line. So it will equal to pressure multiplied to volume 2 minus volume 1. So our volume 2 is equal to 8 meter cube. So as it twicely expands, minus volume, initial volume, it's equal to pressure multiplied on volume itself. So now let's put its physical magnitudes. So pressure 1 equal to 151,500 Pascal multiplied to volume After subtraction, we will have 4 meter cube. And let's calculate. Multiply to 4 meter cube, it's equal to 406,000 joules. It's a result of our problem. What remains now is to investigate the dependence of pressure on temperature of a fixed quantity of a gas in a fixed volume, isobaric process. This gas law was established in 1787 by the French inventor and scientist Jacques Charles. Jacques Charles' law states that the pressure of a gas is directly proportional to its temperature when volume is constant. You can see that according to the graph, pressure increases uniformly with increasing temperature. The graph of pressure versus temperature is a straight line that, when extended backwards, again intersects the temperature axis with 0 Kelvin. In a given picture, you can observe a fixed container with a gas when the temperature of a gas increases. Kinetical energy of gas molecules increase as well. We can observe direct proportionality of a temperature and a pressure of a gas in this example. Here we can see a live application of this law: heating of a gas in any closed container. For example, heating of a gas in a bulb when it's switched on. So, according to our problem, we have a tire. So, inside the tire, we have a pressure. According to manometer reading, it's equal to 2 atmospheres. This is 2 atmospheres, it's only manometer reading, but manometer reading just shows us a difference of atmospheric pressure and pressure inside the tire. Atmospheric pressure is equal to 1 atmosphere, and manometer reading shows us pressure of 2 atmospheres. So, in order to calculate absolute pressure, we need to add pressure that shows us manometer reading. This pressure is known as gauge pressure, plus atmospheric pressure. Therefore, we'll have 2 plus 1. Now our absolute pressure is equal to 3 atmospheres. According to a given of our task, we have pressure 0 is 1 atmospheres. Gauge pressure, I mean the reading of a manometer, is equal to 2 atmospheres. Now we have absolute pressure that equal to 3 atmospheres. Temperature 1 that equal to 0 degrees Celsius, and it equal to 273 Kelvin. And temperature 2 that equal to 30 degrees Celsius, and therefore our Kelvin temperature will be equal to 303 Kelvin. So, in our case, we have a volume constant, therefore we will use equation pressure 1 divided on temperature 1 equal to pressure 2 equal to temperature 2. So, instead of pressure 1, I can write absolute pressure is equal to 3 atmospheres divided on temperature at 0 degree Celsius, and it's equal to 273 Kelvin. It's equal to pressure 2 is ungiven. We need to find it, and its pressure was given at temperature of 30 degrees, that equals to 303 Kelvin. So let me continue my calculation at the next page. So our pressure T is equal to multiplication of temperature 2 multiplied to pressure 1 and divided on temperature 1. So 303 multiplied on 3 atmospheres and divided on 273 Kelvin. Let's calculate our result. So 303 multiplied on 3 atmospheres divided on 273 Kelvin. So our result is 3.329 atmospheres. So students, we identified absolute pressure. However, now let's try to identify gauge pressure. So our gauge pressure, as I said before, gauge pressure, it's manometer reading. So it's equal to absolute pressure minus atmospheric pressure. Therefore, 3.33 atmospheres minus 1 atmosphere, and our gauge pressure is equal to 2.33 atmospheres. It's a reading of our manometer when temperature was equal to 30 Celsius, or in other words 303 Kelvin. Now, dear students and colleagues, I'm going to demonstrate here an isobaric process when volume is constant. For this process, I will use spark system. As for now, it shows atmospheric pressure, conical flask, a beaker. I poured approximately 300 milliliters of water in a beaker, a stand, a clipper to clip a conical flask, and a heater to heat a water inside a beaker. So, as for now, I'm going to connect the spark system that shows a pressure inside a conical flask. As you can see, its volume of a gas is fixed, and I will place it in a clipper. Now, as a temperature of a gas inside the conical flask will increase, a temperature and pressure inside it will increase when a volume will be constant. So, as you can see, water reached its boiling point, and as liquid evaporates, the temperature of a gas inside the flask is increased. Therefore, number of collision of a gas inside the flask is also increased. Therefore, we can see a result of a change of pressure with the help of a spark system that shows as the change of a pressure inside a flask that fixed. So you can see that its temperature increases, pressure as well, but its volume is fixed. This process shows us isobaric process and how does it work. If we combine the results of the three preceding experiments, we see that we have discovered that pressure volume is divided on temperature, and it's directly proportional to the pressure volume 2 divided on temperature 2. It does mean that this equation equal to constant. But what is the value of the constant? To determine that, we repeat all the preceding experiment, and this time, using different quantities of a gas, we discover that the constant is proportional to the number of moles of the gas. Therefore, we have the next equation. We can now measure the pressure, temperature, volume and number of moles for a large number of different gases and calculate the value for pressure volume divided number of moles multiplied on temperature and equal to the constant. This constant is known as gas constant and the numerical value is equal to 8.31 Joule Kelvin divided on mole. Thus, finally, the equation of the state is pressure volume equal to number of moles, gas constant, and temperature in Kelvin. As for now, students, at home you can analyze this graphical change of a macroscopic properties of the pressure and volume and temperature in these graphs. Thank you for your attention and time. And references that I used for this presentation is here.